Let's talk about how we can actually think about functions and surfaces. A function of two variables is a role that assigns to each ordered pair a real number, such as x and y, in a set D, which is a unique real numbers, f of x, y. And D is the domain of f in R2. So the range is a function values of x, y, where x and y are actually in that domain. Z equals f of x, y, where x, y are called the independent variables and z is the dependent variable. Let's take a couple examples. Let's find the domain of f of x, y of 3x squared minus 2y squared. Notice here, there are no stipulations of what x and y can be. So in this case here, your domain would be R2. In the example, f of x, y equals the square root of 3x minus 2y plus 4 over x plus 8. In this case, there are some restrictions. First off, x cannot be -8 because then you have 0 in the denominator. And also 3x minus 2y plus 4 has to be greater than or equal to 0. You can either solve for y if you want to, or you can just leave it like that. I actually prefer to just leave it like that and say D is going to be the set of x, y, such that x cannot equal -8. And 3x minus 2y plus 4 has to be greater than or equal to 0. Another one is, let's look at g of x, y, where equals x squared times the natural log of 2y plus 4x. In this case, 2y plus 4x has to be greater than 0 because you can't take the natural log or the log, for that matter, of any number 0 or less. So we know that's the case. So you can either solve for x or y if you want to. That's really up to you. Or you can just leave it like that and say that D is going to be the set of x, y, such that 2y plus 4x is greater than 0. We can evaluate functions. So let's take f of x, y equals 3x squared minus 2y squared, and let's evaluate that. Let's say f of 1, 4. So 1 came first, that's the x value. 4 came second, that's the y value. So wherever you see an x, you're going to put a 1. Wherever you see a y, you're going to put a 4. So that's going to get me 3 times 1, which is 3, minus 2 times 16, which is -32. So 3 minus -32 is -29. Let's try f of x, y equals the square root of 3x minus 2y plus 4, x over x plus 8. Let's go ahead and evaluate that function at some point. And let's again do this with, I'm going to pick a slightly different one. Instead of 4, 1, 4, I'm going to do 4, 1. So I'm going to, again, everywhere seeing x, I'm going to put a 4. Write that a little bit neater. Everywhere I see a y, I'm going to put in a 1. So that gives me 12 minus 2 is 10 plus 4 is the square root of 14 in the top over 12 in the denominator. We'll try one more. Let's do g of xy equals x squared natural log of 2y plus 4x. Again, I'm going to do g of 4, 1. So everywhere I see an x, I'm going to put in a 4. Everywhere I see a y, I'm going to put in a 1. So we get 16 times the natural log of 2 plus 16, or 18. If I wanted to go graph this, one of the things I want to think about is I'm trying to graph this function z equals f of x, y. So if you think about it, z is your function value along the, we like to think of the vertical axis. If you think about the floor is your xy plane and the corner of your wall is your z plane, your z-axis, I should say, then you can think about having some function here that's drawn, and it's above your domain. So you notice your domain function is in the xy plane, and it the function is over top of that value. And if you take some point here, D, which has an xy value, you can then map it to that z value right above there. So let's go ahead and try to graph some things. Let's look at f of xy equals 4 minus 2x minus 3y. I would like to graph this. So let's just think about when we were normally learning how to graph equations, we were finding the intercepts. So let's do the same thing. Let's find the x-intercept. The x-intercept means that y is 0, but it's not just y is 0. Z is also going to be 0 because we want to be in the xy plane. So x and y are both 0. I'm sorry, y and z are both 0, and you're trying to find out what your x value is. So we're going to put 0 in for y and 0 in for z. And what you're going to end up with is 0 is equal to 4 minus 2x. So therefore, 4 is equal to 2x, so x is equal to 2. Your y-intercept, your x is going to be 0. Your z is also 0, and you're trying to find the y value. So again, you're going to put 0 in for x, 0 in for z, 0 in for x, and then solve for y. So your y is going to be positive 4/3. If you want to find the z-intercept, that means your x and y are 0. And if your x and y are 0, now you need to find out what z is. Well, you're just going to put 0 in for x and y, and you're going to get 4 for your z. So now we have those points, and so now we can go ahead and plot them. So let's start off with the x-intercept is 2, 0, 0. The y-intercept 0, 4/3, 0, and then 0, 0, 4. So here's actually a nice coordinate plane. Remember, the z-axis is the one that goes up. The x-axis is our normal one that we like to think of it going to the right. Actually, I'm sorry. That's not right. That is, think about it as this way. You've got your XY plane normally, which is up and down. You're just going to turn it sideways and kind of rotate it. So this will be the y-axis. And then this axis coming out at you is the x-axis. So we've got the points here. We have the point 2, 0, 0. So we're going to come along the x-axis 2, and then go up nowhere on the y and nowhere on the z. So there's that point there. Then the y value was, the y-intercept was 0, 4/3, 0. So we're going to go nowhere on the x. I'm going to go 4/3, which is about there, and then nowhere on the z. And then the z-axis, the z-intercept was 0, 0, 4. So we're going to come nowhere in the x, nowhere in the y, and we're going to go up on the z. And so you can think about kind of drawing these together, drawing lines that connect these 3 points, and you end up with what looks like a triangle, and actually what it is a plane. So you think about having a piece of paper that kind of follows along that triangle, and there'll just be a plane that goes in that direction. And in fact, anytime you have ax plus by plus c, you're going to get a linear function and basically a plane. Let's do some other ones. Now, we're not going to plot these by hand. We're going to use technology to plot these because it's going to be much nicer with technology. If you go into the course, you can get to the calc plot in 3D link here. This is the URL. I'll copy this and just put it in the notes so you could get this URL if you're not if you're looking at this later and you're not in the course anymore. But that's the URL that you can be using. Sites.monroe.ecc.edu. edu and multivariable calculus. So that's what we're going to be using. We want to do y squared. So again, we're going to come back into this equation here. And we're going to go ahead and go into our 3D plot, calc 3D, calc plot 3D. It always comes up with this picture here, but we can go ahead and change that picture. We want z to be y squared. So I'm just going to type in y squared and use the caret for the square. And there's what it looks like. Now, this kind of looks like a U-shaped. We can think of these having traces. That's what these lines kind of trace out. And if you look at these lines, for every different value along here of what x can be, you've got z equal to y squared. So you get parabolas. So for every x along here, you're going to get a parabola going along from that point. So again, if you think about it, and I can actually rotate this a little bit here, and looking just at the zy plane, you can see you have a parabola coming along here, going through the origin and going up. And so you get this shape, this parabolic shape. These are what are known as traces. These lines here are traces. You also have horizontal lines tracing this way because x can be any value you want. So z equals x being any value means you're going to have lines there. So that's why there's lines tracing this way, and then parabolas tracing when x is any number you want. And so you have these traces and you can get this different picture. So that's what that one looks like. We can look at some other ones. Let's look at the function 9x squared plus 4y squared. So again, I'm going to go back into the calc plot. I'm going to go ahead and hit the home button. Don't know where my home button is on my keyboard because oh, there it is. Hit the home button because I did function and that didn't work. Let's see if that works. Now there's a keystroke that will get it back to where we want, but we can just actually I'll just go ahead and just reload the page. It'll get us back to the normal window once it finishes reloading. Okay, there it goes. And then I'll just change this now to the function I want to plot, which the function I want to plot, if you remember, was 9x squared plus 4y squared. So we're going to type in 9x squared plus 4y squared. And there's what the plot looks like. And again, you can look at this and you can see that it kind of looks like a little bit of a bowl. And in fact, what I'm going to do is I'm going to change my x and y here a little bit. I'm going to actually change where I want the z's. No, I don't want to change the z's, but let's just change the x and y just a little bit. Maybe we'll go I'm trying to decide how I want to change this now. Okay, whoops. We'll do x min is -1, whoops, -1, and y min is also -1, and z min is -1. Oh, there we go. I can just change my z max. We'll just change our z max to 1. I don't know why that's not working. So you can just pick the first octant if you want, or positive z's. So let's pick the positive z's so we don't see the x's. And now you can see sort of, it really does look like, it's like a cup. So this actually looks very much like a cup. This is known as elliptic paraboloid because you've got this elliptical shape here. If you were to look down on top of it, you see you have an ellipse. So that's why we learned about these. You have an ellipse here. And in fact, if you look at your traces along that direction, you can see kind of you've got these ellipses going here. And then you can see your different traces in different directions will give you those different shapes. And in fact, you can see you also have hyperbolas going on here, or parabolas going on here. So that's why it's called elliptic paraboloid, because you've got your parabola shapes here, and then you've got your elliptical shapes this way. So that's what you've got here. So we know that that's what this shape looks like now. So we can actually label this one as an elliptical paraboloid. Let's look at another one. Let's look at this graph here. It's x squared minus y squared. So I'm going to go ahead and look at, and by the way, I should go back to this just a moment. If I think about this is 9x squared plus 4y squared. If you thought about that just equaling like 5, you'd have an ellipse. So you can see that along the z-axis, you do in fact have those ellipses going here. So you can see that's what's happening. So let's look at this one, kind of think about that same idea. Here you see if you have z equal to just constants, you're going to have hyperbolas. So let's see what that gives that shape. So I'm going to go back. I'm going to go ahead and now if I go back and look at what my function was, it was x squared minus y squared. So I'm going to have x squared minus y squared. And this is the interesting shape you get from this. And you can zoom this around a little bit, move it around, see what it looks like in different places. You can also use arrows to arrow around and look around. You can use up and down arrows to move around a little bit. You can do the shift and just go along a certain axis to see what it looks like. And you can see in your traces, if I look just along this axis here, where I'm just looking along the x-axis, I can see I have hyperbola looking shapes there. If I come over here, I see I also have nice little hyperbola looking shapes here. So you can see you've got those parabolic shapes going on here. And you can also see you have hyperbolas happening there. So this one's actually called a hyperbola paraboloid. Because you have the hyperbola shapes. And you've got those hyperbolas opening up. All right, let's do one more. Let's look at 9x squared plus y squared over 4 plus z squared over 9 equals 0. You actually can still plot these. So we'll come over here and we're going to type this one in. So we have, because I can never remember which one I just typed here, we're going to have x squared plus y squared over 4 plus z squared divided by 9, oops, equals 1. I guess I can't do that, but I can actually draw in implicit surfaces. That's what I need. I didn't do an implicit surface. There we go. So I did an implicit surface. It almost is what I have. So it looks like basically what I have, except I don't want it over 9. Let's just make this one just z squared. So they have example ones you can put in here, and you can see that one's there. Now we can hit enter. Let's turn this one on. Okay. Oh no, that's the one I want on. Okay, that's the one I want to go. There we go. There it is. And now you can see your shape here and what that shape looks like. I'm curious. I do want this one divided by 9. I want this one divided by 9. And I want the y squared divided by 4. Oh, I want plus. That's why my mistake is. Okay. All right. So now we're going to graph this one up. There we go. So there's what it looks like. I'm going to let the z's go all the way to, let's go 10 to 10. And when I do that, and I'm going to let my y's go a bit farther out, I'm going to take those out to 10 to 10 also. And what you see is you get basically, it looks like almost like a football. And this is known as an ellipsoid. So this graph here is an ellipsoid. There are lots of other these graphs you can see. And again, you can kind of see those layers in your graph. If I come back to this graph and see them, you can see we've got ellipsoids going around this way, ellipsoids coming around this way, and ellipsoids going around that way. So you can see you basically have all of these nice little ellipsoid layers you can see, and that's why you get this thing called an ellipsoid. There are lots of other things like this. There's a table in your book on page 679. Please get to look at that one and see what those are. We can actually classify these and see what they might be. Here we have x squared plus 4y squared plus z squared minus 2x equals 0. And I'd like us to classify this. And because the x squared and the y squared and the z squared are all there and they're all positive, this one will be an ellipsoid. Okay,